All right. Hello, everybody. I am going to be doing a review for exam one. So we're going to start off with 2.1, and that was quantities and variables. So this is what we started the course out with. So I'm going to change the color. A quantity is just some measurable attribute of an object or situation. So some are fixed, some vary or change. Examples of measurable attributes would be, for example, my height in inches, right? To describe a quantity, we need the object or the situation. We need the attribute, so height, distance, time, but we also need to be specific. So what is our unit of measurement for that? And sometimes we'll also need a direction, especially when we're talking about distances, okay? So some good examples of variable definition, or excuse me, quantity definitions are the number of seconds. So we have a unit here, and we're describing time, right? So this is a time since the ball was thrown. And so then this is describing our situation. So here's our time, our attribute. Here are our seconds, those are our units. And since the ball was thrown is sort of describing the situation. Okay. In this one, we have our attribute, which is distance. So this is the attribute. The distance in feet, so we have a unit here, in feet, between the fielder and the ball. So this is describing both the situation and the direction. Awesome. So some bad examples would be if you just said time. Of what? So what is the situation? Is it time since my day started? Is it time since classes started? We'll need a starting point there. So need starting point. And units, of course. So what? Is it hours? Is it minutes? Is it seconds? Days? Years? Centuries? Right? Our second bad example is number of seconds. So we have a unit here, and we have the attribute. We have time, but since what? We need a starting point. So we still need starting point. Next attribute, or our next definition, was distance. Again, same issue here. We need a situation or object, because it could be what? The distance between the fielder and the ball. It could be the distance between me and the wall. So we need the situation and object. And we need units, of course. So what is this distance in feet, in inches, in yards, and let me try to think of some other units, in millimeters. So be more specific. And then finally, almost good, time since the ball was thrown, really good. We have our situation and direction, it's very clear, but we need what units? So was it seconds? Was it hours? So on and so forth. So a variable is just a letter or symbol that represents the values of a quantity. So if we have our variable t here, that could, for example, be representing the values of the quantity of seconds since the ball was thrown. And for example, if we had a variable, let's say r, this is our variable here, we could say that r represents values of the radius in centimeters of a ripple, if you did this example in class. Okay. So we're moving on to 2.2. Not too many example questions for that, because you'll kind of get practice with all of them. But now we're going to be talking about change, right? So this symbol, this little triangle right here, as we remember, means is called delta, and it means change. So if x is a variable, and again, that means it represents the values of some quantity, then this delta x is read as change in x, okay? So if we know a starting and ending value for x, we can calculate that, right? It's just our final value minus our initial value. So as an example, if we're going to let a be the amount of money in your bank account, and let me just make this a bit more clear that it's a, right? So a is the amount of money in your bank account. And I tell you that yesterday you had $4, and today you have $27, which same. What is the change in your balance during this time? Well, I end up with $27. And I started with $4, right? So I had to have gained $23. And this is our change in A, right? Our change in the amount of money in our account. So if we have two variables, now we're going to be talking about what in terms of means. So if we have two variables that represent some quantities, so let's say x and y, these are variables that represent the values of some quantities, and they're related, so they change together, so they're related. so that we can express the values of y based on the values of x with an expression using x, we say that the quantity that y represents is expressed in terms of the quantity that x represents. And so for an example here, the quantity y here is alone because it's represented in terms of x. So here could be something in terms of x. Let's say y equals 4x, plus 3. We could have y equals, we could have y equals x, honestly. We could have y equals x squared minus 3x. Anything here, as long as it only involves x and tells us how to get values of y based off of x. And so for that reason, y is called our dependent variable because it depends on x. And so x is then our independent variable because we can kind of vary its values, and in response, y will change. So y changes in response. So as a little example, let's look at the square. We want x to be the length of the square. We want p to be the perimeter of the square. And we want a to be the area of the square. And all of these are in centimeters and centimeters squared where appropriate. So let's draw this square. So we know that our side lengths here are going to be all x centimeters, right? So x, 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 x. Our first question asks, write an expression for perimeter in terms of side length. So I know that in terms of side length means that x is going to be my independent variable, right? And perimeter is going to be my dependent variable. So I need to say, what does perimeter equal in terms of x? Well, that's just 4x. Okay. You also might see it written, write an expression in terms of area for side length. And in that case, we'll have to be careful because it says in terms of area. And so side length is then going to be our dependent variable. So x here is actually going to equal something in terms of area. So you have to look where the in terms of is attached to. So in terms of what? In terms of area. So areas are independent variable. And this one, in terms of side length, x was our independent variable. Okay. So the area of this square, area is equal to x squared, right? And so if we want to kind of reverse this, if you've been doing your inverse functions, you sort of know how we do this. Well, then we know that x is just equal to the square root of the area, right? So if I had a square here and the area was 4 centimeters squared, you know the side length is 2, right? You took the square root. If the square had an area of 9 centimeters squared, you know the side length would have to be 3, so on. And so x is going to equal the square root of a. Okay. Now, the coordinate plane and graphing, I'm going to let you guys read this on your own. It's also in your workbook. I would say that that's a really great resource, right? But basically, we can graph two quantities. And this point right here, 4, 3, would mean that when the value, excuse me, oh my goodness, it did not like that, okay? This means when the value of our independent quantity is 4, then the value of our dependent is quantity is 3. Okay. And so it's really important to get the order right here. So when the value of our independent is this, then the value of our dependent is 3. We can only say that the independent changes the value of our dependent, not the other way around. Okay. As an example, let's suppose we have this graph right here that represents the depth of a puddle in feet in terms of time from now in hours. So in terms of time from now, what is our independent variable? Think about that for a second. So what values is going to change what other value? So our independent value, what's going to lie along here is time, right? Because we're going to represent the depth of the puddle in terms of time. So depth in terms of time. So depth is going to be alone here, and it's going to equal something in terms of time. And then if I have this graph right here, the independent quantity is time, and the dependent quantity is depth. And again, be more specific. Technically, the independent quantity is, again, time from now in hours, depth of a puddle in feet, but I'm just going to shorthand them here. Now, our third question asks us, what does the point 12, 1 mean? Well, that means when 12 hours have passed, right? So after something has happened to our independent quality, when 12 hours have passed, the depth of our puddle is 12 feet. Okay, that's not 12 feet, excuse me, is 1 foot. Careful there, right? So 12 hours in, the depth of our puddle is at 1 foot. Okay. Again, I'm not going to do any more examples because all of the questions in the exam review will help you with this concept. Okay. Moving on to constant rate of change and linear functions. This is going to be a really, really, really important topic for this whole course, right? And so this exam will have a lot of questions on it. Your future exams will have a lot of questions on it. This is a really important concept. So if you don't have this nailed down, please do some practice problems. So if x and y are the values of two quantities related by a constant rate of change, then over any interval from x1 to x2, where y changes from y1 to y2, so we can draw this out here. So x1 to x2, and then y1 here all the way to y2. So any interval, so we could have one and you can change these intervals as you want, but as long as the y value, so this change in y that results from our change in x, the ratio delta y over delta x will always have the same value. And we use m to represent this value. So here's our delta y, or here's our delta x. Let's draw that first. Here is our delta y. What we're saying is delta y over delta x is always a constant. Or in other words, delta y is always m times as large as delta x. So we can multiply both sides of this by delta x, right? To get delta y equals m delta x. And so our change in y is always m times as large as our change in x. These are equivalent, right? Real quick, I want to go over the point slope formula. This is the, whenever you have two quantities that are related by a constant rate of change, what that you can also take that to mean is that the two values have a linear relationship. And you've worked with linear functions before. I think like y equals mx plus b. This is our slope intercept form. We have our slope and our intercept. But sometimes it can be easier and more enlightening to write it using this point slope formula. So if x and y are related by a constant rate of change, let's say m, this is delta y over delta x, and y equals y1 when x equals x1. So in other words, this point x1 comma y1 is on our graph, right? Then y minus y1, or any change in y from y1, right, is always going to be m times as large as any change from x1, right? So this could be delta x. And so you can literally write y equals m times x minus x1 plus y1. And this would be the equation of y in terms of x, okay? So let's do a concrete example. Let's say this point 3, comma negative 3.65 lies on a line with constant rate of change negative 1.75. So I think it's helpful to draw this out. 3, negative 3.65, so negative 3.65 here. 3 is here. We have this point. And it has a constant rate of change of negative 1.75. So when x changes by a certain amount, let's say x changes by 1, so from 3 to 4, then our y will change by negative 1.75. So this will be, cannot do math that fast. Let's see. So this will be negative 3.65 minus 1.75, right? So negative 5.4. This change in y is negative 1.75 times as large as our change in x, which was 1. And so we'd have something that looks like this, right? This is just a picture to help you kind of think about this problem, but it's not necessary. We can answer these questions without the picture, but sometimes it can be nice to draw a picture out. If the change in x, and let's write that down, so delta x is 4.2, what is the corresponding change in y? Well, I know that y, our change, or excuse me, our delta y is always m times as large as delta x. So our change in y is always negative 1.75 times as large as delta x. That means my change in y is just negative 1.75 times 4.2. That would give you your answer here. You can calculate that out, but this is the answer. Okay, now it's asking when x is 1.8, what is the corresponding y value? Okay, so we have to think. So we have the 0.3 comma negative 3.65, and we move to the point 1.8 comma something, right? So y. Well, what is our change in x here? Well, our final point is 1.8, and our initial point was 3. So 1.8 minus 3, or our change in x is negative 1.2. And again, we know that our change in y is m times delta x, or negative 1.75 times delta x, so times negative 1.2. Let's calculate that out. So our change in y is going to equal 2.1. Or in other words, the value 1.8, comma, negative 3.65 plus 2.1, right? So that's our change in y. We add 2.1 more units. Or the point 1.8, comma, more math, negative 3.65 plus 2.1, negative 1.55. So this would be our answer for this one. And now we want to define a function j. And so we're going to use function notation here. We haven't reviewed that here, but I'll post another video from another professor who's going to help us with that. That expresses the value for y in terms of the value for x, right? So going back to the formula we had here, we can say that j of x equals y. And so we need a formula that turns x into those y values. Well, that's just going to be m times x minus x1, so negative 1.75, times x minus, what is a point we have on our graph? We have this point, 3 comma negative 3.65. So x minus 3, and now plus our y value at this point, so minus, or plus negative, so plus negative 3.65. Or in other words, negative 1.75, x minus 3 minus 3.65. And this would be your equation. Okay, we're going to do more practice. Again, this is a very, very important one. This one is asking you to find the constant rate of change of y with respect to x given this graph. And we've gone over this in class a few times, and I'm sure you've seen this on your homework. How do we do this? So remember, delta y equals m delta x. Our constant rate of change is just telling us how many times can delta x, or does delta x, fit in to delta y? Or how many times as large as delta x, or I guess, yeah, I'm going to write it like this. Delta y is how many times as large as delta x. So in this case, here's my delta y, and here's my delta x. How many times bigger than delta x, or how many times as large as delta x? So if I were to stack delta x's on top of each other, boop, 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 how many would I need to stack in order to get my delta y? How many times as large as delta x is delta y? Well, I hope you would come to the same conclusion, but I think that delta y is just twice as large as delta x. So delta y equals 2 delta x. So the constant rate of change is 2. Yippee! And I honestly use that formula to find the constant rate of change. So that's the formula right there. Okay, so if we have this point, y equals 2.5 when x equals 1, so 1 comma 2.5. What is the value of y when x equals 1.2? Okay, let's think this out. What is our change in x here? Well, we go from 1 to 1.2. So our change in x is 0.2. And so then our change in y is just twice that, or 0.4. So 2 times delta x, which is 0.4. And so then our y value is just going to be our initial, so 2.5 plus 0.4. It's just 2.9. Okay. So if delta y equals 2.5 when x equals 1, let's write a formula that expresses y in terms of x. We can go back to our equation here or derive it yourself. Y is equal to 2 times x minus 1 plus 2.5. And if you're confused on how I got that, go back to the previous one and try it yourself. So in this relationship, is it true that the value of the varying quantity y is always 2 times the value of the varying quantity x? Take a look at this graph. Would you say that y is always twice as large as x? The answer is no, right? For example, I can write out, let's see, this point right here, right? Here is our y value, right? Here's y, and here's x. And so in this case, I would say, yeah, y is about twice as large as x. But let's take a look at this case right here. Here's our x, right? So it's going to be this direction. Our y value is 0 here, but that's not twice as large as x. We would want y to be all the way down here, right? And so we don't have that y is twice x, but we do have that the change in y is twice the change in x. And so we're going to talk about proportionality now because they're very related, right? So two quantities are proportional when one is always a constant times as large as the other. So let's take a look at this system right here. So I would say, and let's say if my estimation skills are good, the length of segment A is about half as times as long as the length of segment B. And the length of segment B is twice as long as the length of segment A, right? And so what if this was a recipe? Let's say A is cups of flour and B is cups of water. And I tell you that normally in the recipe, there's 1 cup of flour and 2 cups of water. You're making bread, let's say. Very watery bread. Well, if I wanted to double the recipe, I could double A and I'd also have to double B. And so we would go to 2 and 4, right? And so that's the difference between proportionality and constant rate of change, is in one, this A will always be twice as, or this B will always be twice as large as A. But in constant rate of change, just the changes in these values will always be a constant times as large. So that's a word vomit, honestly. Let's do an example. A bucket is filled with water up to the 7-gallon mark. The bucket springs a leak. So let's draw this. And begins draining at a constant rate. So the bucket is filled up with water to the 7-gallon mark. It springs a leak and it begins draining at a constant rate of 3/8 of a gallon per minute. So it's initially at 7 gallons, but then, oh no, water starts leaking out. And so water is leaking out at 3/8 of a gallon per minute. And so we want to determine some quantities in the system, right? So first of all, we want a function that determines the number of gallons of water in the bucket. So N in terms of the number of minutes. So in terms of time that the water has been draining. So let's call this f of t. And I know that I start out with 7 gallons in the bucket, right? And that every minute I lose 3/8 of a gallon, right? In other words, if t is my number of minutes since the water's been draining, I will have lost 3/8 times t gallons, right? So 3/8 of a gallon per minute means that after 1 minute, we've lost 3/8 of a gallon. After 2 minutes, we've lost 6/8 of a gallon. After 8 minutes, I've lost 3 whole gallons, right? So, and then where f of t equals n, right? Okay, but is n proportional to delta t in this relationship? Let's think about that. A really short time, let's say, here's our amount of water. We have 7 gallons left, right? When the time is 0. Or actually, I'm going to draw after a minute, right? So let's say a minute has passed. So when n equals 1, when t equals 1, when t equals 1, n is equal, the number of gallons left in the bucket is, actually, let's do 3. Sorry, I keep changing the numbers. After 3 minutes, not 3 minutes, 8 minutes. Last change, I promise. After 8 minutes, how many gallons are left in the bucket? Well, we're losing 3 gallons, or 3/8 of a gallon a minute. After 8 minutes, we've lost 3 gallons, so we have 4 gallons left. Okay, but if they're proportional, that means when t equals 16, I should have, so to get here, there's half as much, right? Then that means that I should have n equals 8 gallons of water. Is that true? Do I suddenly have more gallons of water than I started out with? No, absolutely not. I actually have even less gallons. I have 1 gallon of water left. And so in this first one, n is half as large as t. And in the second one, n is a 16th as large as t, right? And so they're not proportional. On the other hand, because they're related by a constant rate of change, we know that delta n is just equal to negative 3/8 times delta t, right? The change in gallons of water is just negative 3/8 times our change in time. After 1 minute, if 1 minute has passed, we've lost 3/8 of a gallon. If 8 minutes has passed, we've lost 3 gallons, right? Delta n and delta t are proportional. Because no matter what, delta n is our change in gallons of water is always going to be a constant times our change in time, right? Okay. Part D asks us to say if D represents the number of gallons of water that have drained from the tank t minutes after the water began draining, is D proportional to t? So let's take a look at this picture and think about it for a sec. What is D in terms of t? If I told you after 1 minute how many gallons have drained. So I know that D equals 4, or not 4, excuse me, D equals 3/8 after 1 minute, right? When t equals 1. 3/8 of a gallon is drained after 1 second. And I know that D equals 6/8 when t equals 2, right? Well, D is just equal to 3/8 times t, right? In other words, the amount of water we have in the bucket, f of t, or let's just say n, right? N is just equal to the gallons that we start out with, 7, minus however many gallons have drained, minus D. So D is just 3/8 t. And so they are proportional because D is just a constant multiple times t. Okay. As seen before, if x and y are related by some constant rate of change, then their change in y is always m times as large as change in x. Delta y equals m delta x. And so our change in y and change in x are proportional. But they don't, but even when that is the case, y and x themselves don't have to be proportional. Look at our previous problem. They can be, so for example, with D, but they don't have to be. So that's something to keep in mind. Okay, a good practice problem is number 28. We're supposing that this formula, h equals 12 minus 2.5t, is defining the remaining height, h in inches, of a burning candle. So this is the remaining height of a burning candle in terms of the number of hours that the candle has been burning, right? So what is the meaning of 12 in this context? Well, that's just going to be the initial height of the candle, right? After no time has passed, when we just light it, this is the initial height of the candle. Okay. What is negative 2.5 in this context? Think about this using the language of constant rate of change. And I sort of gave it away. This is just the constant rate of change of our height with respect to time, right? So after a certain amount of time has passed, or after a certain number of seconds has passed, negative 2.5, our candle length has changed by negative 2.5 times that amount. So after 1 second, our candle length has decreased by 2.5 inches. After 10 seconds, or not 10, I guess we can't do 10. After 2 seconds, our candle has decreased by 5 inches, right? So what is the meaning of negative 2.5 t? Well, that's just going to be how much has burned off, right? How many inches, or how many inches? Let me change that. How many inches have burned off, right? Okay, right? So our initial height minus how much is burned off, right? So minus how much is burned. So second question asks, is the point 2, 8 on the graph representing this relationship, why or why not? Well, let's check. So we know that the point 0, 12 is there, right? So when we first start burning the candle, all 12 inches are left, right? And so to get to 2, well, what is my change in time? How many minutes have passed? 2 minutes have passed. So 2 minutes, which means our change in h is just going to be negative 2.5 times our change in t, right? Or in other words, 5 inches have burned off. So 12 minus 5, this is equal to 2, 7. That's not a point on our graph, right? Because after 2 seconds, our candle is actually, let me draw this a little bit better. After 2 seconds, our candle is 7 inches tall now. 2 seconds, because we've decreased by 5 inches, right? And so no, this is not on our graph, because after 2 seconds, our candle is not 8 inches tall. It is 7 inches tall. Okay. This is our largest section, and I would say, again, there's a reason why. It's very important, super helpful for every math that you will take for the rest of your life. But let's move on to average rate of change, okay? So the book describes average rate of change of a function over some interval of the domain to be the constant rate of change over that interval x to x2 that produces the same net change y2 minus y1 in the function's output. Or in other words, let's take a look at this graph. If we have these 2 points, x1, y1, and x2, y2, then no matter what our function is, it could be this, it could be this, our average rate of change is just the slope of the line connecting these 2 points. That's all it is. And if you were in my class, I did the demonstration with one of our students about just like cruise control, right? If we travel the same amount of distance in the same amount of time, no matter what our path looked like, we had been going at the same average speed during that time interval, okay? So if y equals f of x, so if we have function notation now, well, then this is just f of x2 minus f, I guess I didn't do the actual formula here, right? The slope between these 2 points is just our change in y, so y2 minus y1, over our change in x, x2 minus x1. And so when we have a function, our change in y is f of x2 minus f of x1 over our change in x, right? So we're going to do this problem as an example. We're going to let d be the distance in feet of a race car from the starting line. And we're going to let t be the number of seconds since the race began. The distance, d, is a function. So d is the distance in feet of a race car from the starting line. T is the number of seconds since the race began. Distance is a function of time and is represented by d equals f of t, which is given by this. And so you can graph this yourself and check out this problem. But what is the meaning of f of 7 minus f of 3? So this is his distance after 7 seconds minus his distance after 3 seconds, or 3 seconds, excuse me. That's just the distance he's traveled between 3 and 7 seconds. Or his change in distance. So change in distance, you can use English, lots of ways to interpret this, right? And now we want to compute the car's average speed over the interval from t3 to t equals 7 seconds. So let's check that out. Well, again, we're going to want to do our change in distance over change in time, so f of 7 minus f of 3. We're going to want to divide that by our change in time, so 7 minus 3. Let's calculate this. So you can use your calculators at home to check this. But I'm going to do that here. So it hates me, so give me just a sec. Guess this is a great opportunity to try it on your own, because my calculator does not like me right now. So I got 140 feet, and that could be wrong because my calculator is being fussy right now, but f of 7, I got to be 177.8 feet. And f of 3, I got to be 37, excuse me, do not move that. I got 37.8 feet. And so when we subtracted those two, I got 140 feet. Divided by our change in time, there are 4 seconds between those two intervals. So between 7 and 3, 7 minus 3 is 4. We calculate that out. We get that his average speed was 35 feet per second. And so for part C, again, oh, my screen sharing is paused. That's awesome. Lovely. Love that that hasn't been paying attention. The best meaning of average speed in this context is the constant rate of change he would have to be traveling. So the constant rate of change or the constant speed he would have to be traveling to go between 37.8 feet and 177.8 feet in 4 seconds. Okay, so on to our distance and circle formulas. What is the distance between these 2 points, x1, y1, and x2, y2? Well, let's split this up a little bit into a triangle so we can use the Pythagorean theorem, right? Well, this distance right here is just y2 minus y1, our change in y. Actually, I'm not going to say that, but you can if you want to. And then this distance right here is just x2 minus x1, right? And so by the powers of the Pythagorean theorem, we know that d squared, so c squared equals a squared plus b squared, or a squared plus b squared equals c squared. Let's write it like that. Well, then that means that x2 minus x1 squared plus y2 minus y1 squared equals our d squared, right? And so taking the square root of both sides, we're going to get this, that our distance is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. And so a circle centered at a comma b with radius r is all of the points x comma y, so that the distance between xy and ab is equal to r. So if this is a point xy, then the distance is r, and that's the case for any point here. So the distance between a and b and here is r. The distance between a and b and here is r. Or in other words, going back to what we had before with our Pythagorean theorem, x minus a squared, our distance between x and a, plus y minus b squared, that's our distance between y and b, is equal to r squared. And so let's consider this circle. Let's use a real circle. So it's centered at negative 2, 5. And there is this point, 4, 12 on the circle. Okay. My very first thing, let's calculate the radius, right? what is this distance right here? And let's break it up using our Pythagorean theorem. So to get from -2 to 4, that's 6. So 4 minus -2 equals 6. This vertical distance right here is going to be 12 minus 5, or 7. No, am I wrong? That's definitely wrong. No, that's 7. Okay. And so we need to figure out what this is going to be. And so we say r squared equals 6 squared plus 7 squared, right? So r is the square root of 6 squared plus 7 squared. Put that in your calculators. I'm going to get that this is equal to around 9.2195, okay? And so my radius, this is my radius, 9.215 units. So area of a circle, if you recall, is pi times the radius squared, or pi times 9.2195 squared. Put that in your calculators, 9.219 squared. You get 267 pi. Gibby. So our next question is asking, is the point -6, 14 also on the circle? Well, let's check that. It just needs to be a distance of this 9.2195 away from the center, this 25, right? So let's check. So -2 minus -6, that would be our x distance. So square that. Plus our 14 minus our 5, right? This is our distance right here. Between 614 and, oops, I've made a grave error. Let's do that, change that. I guess it's not technically super grave, but it could cause a bit of confusion, and I don't want that. -2, 5. Right, so the distance between this point and this point, I'll write the first coordinate first. So -6 minus -2, there we go. So this is the square root of -6 minus 2, this is -4, quantity squared, plus 9, quantity squared. If you calculate this out, you will get a value that's not the same as this value right here. And so it does not lie in the circle, which is not equal to 9.295, because it's a little bit more. It's actually somewhere like out here. So it's not on a circle. And so going back to this equation we had here, what is the graph of our circle? An equation for our graph? Well, that's x minus our x center point. So x minus -2, quantity squared, plus y minus 5, quantity squared, is our radius squared. So 9.2195 all squared. Or in other words, x plus 2 squared plus y minus 5 squared equals, if we would actually calculate it out, so that is equal to 85. Okay. So 2.7, we're on to absolute value. So the absolute value of x gives us the magnitude of x. So the absolute value of 1 is 1. Absolute value of -2 is just 2. Absolute value of pi is pi, and absolute value of -100 is 100. And so you might be tempted to just say that the absolute value of -x is just x, but this is not true, right? Because what if I put -1 in for x? Well, then you are trying to tell me, well, not you, but if you were trying to say that this was true, then you would be telling me that -1, or the absolute value of -1 equals -1. That doesn't make sense. So be careful. It tells us the magnitude. You cannot just take the negative sign out, okay? So the absolute value of x minus a gives us the distance between x and a on a number line. Why do we need the absolute value? Well, if x is to the left of a, then this is a minus x. And if x is to the right of a, this is x minus a. So we just kind of have to be careful. It's easier to just use absolute value, because that way we just don't have to worry about our signs, right? But that's useful for us to read are these inequalities or equalities, right? So if I told you that the absolute value of x minus 1 equals 3, you could go, what the hell? Or you could say, oh, this is my distance between x and 1, x minus the absolute value of x minus 1, and that distance is equal to 3. In other words, x is 3 units away from 1, and so x can be negative 2 over here, or it can be 4. These are my x values. Now, what if we have a plus in here? So the absolute value of x plus 2 is less than 7. Well, the absolute value of x plus 2 is the same as the absolute value of x minus negative 2. And so this is just the distance between x and negative 2. Distance between x and negative 2. And I'm saying that this, remember, alligator eats the bigger one. This is less than 7. What does that mean? Well, let's put some points here. So negative 9 is 7 units away from 2. And also 5 is 7 units away from negative 2. And if the distance between x and negative 2 is less than 7, well, then I know it can't be 9 or 5, right? So I'm going to put holes there. But it can be any of these values in between, right? X is less than 7 units away from negative 2. So x is between negative 9 and 5. And this one, x equals negative 2 or 4. And finally, we have something like this. The distance between x and, the absolute value of x minus 13.2. Well, again, we can read that as the distance between x and 13.2 is greater than or equal to 0.1. So it's at least 0.1 or greater than or equal to. Gotoet. Or in other words, x is 0.01 or more, 0.01 or more units away from 13.2. So in other words, if we have 13.3 here and 13.1 here, x can be either of these values, because that's at least 0.1 units away, or any of these values over here, right? And so this is saying that x is less than or equal to 13.1, or x is greater than or equal to 13.3. Okay, I hope that's clear. We're going to do some practice problems, and then we're finished. So question 40 asks us to express the following scenarios by using an absolute value equation or inequality. So remember, absolute value of x minus a is the distance between x and a. So we also want to express it using interval notation and as an equality. So I'm going to go back here, actually. This is the interval negative 9, comma 5. Negative 9 and 5 are not included, so we use open brackets. This one is anything all the way from negative infinity up to 13.1, and that's included, so we use a closed bracket, unioned with 13.3 all the way to infinity, right? And again, 13.3 is included. Okay, so part A, and I'm going to write this down here. So 40A, the ideal weight for a bag of cookies is 520 grams. So I'm going to draw my number line, and I already know that 520 is my ideal weight, so I want to be near there. So 520 grams. The actual weight, so the ideal weight is 520 grams, and the actual weight may vary by no more than 10 grams. So it can vary by 10 grams or less. Let's look at that here. That means that I can have a bag of cookies with only 510 grams of cookies, which would kind of suck. Or I could get lucky. I could have a bag of cookies that has 530 grams in it, right? But I can't have anything outside of here, right? They won't let that happen. The cookie company got my back, right? So, in other words, it's all of the values in here, right? And does that include 510 and 530? Yeah, so 10 grams or less, so I can include these values. And so that means that our actual weight is between 510 and 530. And in interval notation, this is 510 to 530, and they're both included, so we use our closed brackets. Yippee! Moving on to part B, we'll do this in black so it's a little easier to see. the set of values for the variable x whose distance from 3 is more than 0.6 units. So let's put 3 here. So distance from 3 is more than 0.6 units. So I know that 3.6 is here. And 2.4 is here, right? That's also 0.6 units away. Are 2.4 and 3.6 possible values of x? Is their distance more than 0.6 units away? No, those distances are exactly 0.6 units away. So there's holes here. We don't include them. But anything farther away from 3 is fair game, right? So that includes all of these values down here. So then this means that x is less than 2.4, not included, or x is greater than 3.6. Okay? And in interval notation, this is negative infinity all the way to 2.4, which is not included, so we use our open bracket. Unioned, I'm going to put that here, unioned with 3.6, also not included, so we use an open bracket, all the way out to infinity. Okay. On to 41. So we're going to solve each of the following absolute value equations and inequalities. We want to use interval or set notation again, and I'm going to do both because I think it's helpful. So part A is saying the absolute value of x plus 5. What is that? Think about that in terms of distance. That's how far away. So x, or the distance, right? The distance. So part A. This is the distance between x and negative 5 is less than or equal to 12. So let's draw our handy little line. Also very good practice to draw these lines. It's very helpful. So we have negative 5 here. What's 12 away from negative 5? Oh boy, can I do math? 7. And in the other direction, we have negative 17. Do I like that? I guess that's right. Okay. And so if the distance between x and negative 5 is less than or equal to 12, I know it has to be in here, in this range, right? So this is the inequality that x is smushed between 17 and 7, or negative 17 and 7, included, so less than or equal to we use here. Or the interval negative 17 all the way to 7, endpoints are included because it's less than or equal to, right? So part B is saying the absolute value of x minus 3 equals 8. So again, this is the distance between x and 3. We're saying that's equal to 8. Let's draw a number line. So we have 3 here. 8 more than 3, so 8 units away in this direction, we have 11. And 8 units away in the other direction, we have negative 5, right? And so if the distance, the distance between x and 3 is exactly 8, well, then x equals negative 5, or x equals 11, right? Has to be one of these points. And finally, for part C, our absolute value of x minus 6 is greater than 4. That means the distance between x and 3, or excuse me, x and 6 is more than 4. So let's draw our line. 6 here. 4 away is 10. Another 4 away is 2 in this direction. We know that x has to be more than 4 away, so it's somewhere out here. 2 and 10 are not more than 4 away. They're exactly 4 away, so they're not included. So this is negative infinity all the way to 2, not included. Union with 10 to infinity. And we can also say that x is less than 2 or x is greater than 10. And we're done. I hope this has been helpful. And this should be posted with another video for module 3, which will be linked in the description. If it's not, I don't know, actually. Come back and check for when it is available. Yeah, I hope this has been helpful. Thanks, everybody.